It's okay. Just see what you can do. Linear function, one everybody knows and loves. We're going to talk about key features of these, because what happens, ultimately you want to be able to hand sketch these and then move them around, shift them around. So just the ability to sketch it just basically is important, because you can do the transformations, move this around, and then the way you construct it is the same no matter where it's placed on the graph. So you guys know a line is up 1 over 1 from wherever it's located, and that's the same line you've always known. Domain and range in this case, you can put in any x. It goes all the way to the left, all the way to the right for the domain, and all the way up and down for the range. Then if you go to the, and remember that these look the same, but they represent different things because of the context they're in. Domain is x values, small to big. Range is y values, small to big. Remember, you always put the smaller number. A bigger negative number is a smaller number, and I know that's a really common mistake. I know you guys are doing practice problems with domain and range, and sometimes you'll put, for instance, if it's between like -10 and 2, +2, a lot of times those will get switched around because you think, oh, small number on the left, big number on the right, but a bigger negative number should go on the left. It's the smaller number as in on the number line, more negative. All right, to the next one, quadratic, you know and love. X squared is the function. Domain on that one's all real numbers. It goes left and right all the way. And then up and down, though, this range business, take note, it does touch at 0, 0. And somebody asked that question yesterday. Does it touch there? That's the right idea. You want to know real details like, does it touch at a particular spot or not? Because it has everything to do with your range, if it's going to include a bracket or not. And this one does. So that's the range of that one. Good old cubic, x cubed. Everyone remembers this one too, kind of that snaky graph. It's all real numbers for both, negative infinity to infinity in both cases. Okay, if you need pausing, go for it. I know I'm talking fast. I've also loaded the video up to Google Drive, and it's on my YouTube channel, etc. Okay, but we're going to cruise on. The next one is, let's talk about key features of these. So on the linear and quadratic, I pointed out some of the key points you would need to freehand draw. Linear, pretty known, up 1 over 1, just plotting points at a slope of 1. The quadratic, it does touch at 0, 0. And then from that, we call that the vertex. And so once you know the quadratic's vertex, then you can move over 1, up 1 to plot a point, and then over 2, up 4 to plot a point. And that's not a slope issue. Remember, we're squaring the number. So 1 squared is 1, 2 squared is 4. That usually is enough to get a decent sketch of a quadratic. And then the symmetry of it means you can do duplicates on the other side. You can always just graph one side of a quadratic or plot one side, then go to the other side of the axis of symmetry and do 2 more, or more. You can do as many points as you like. Let's go to the reciprocal function. This is where I don't know if your notes are in the same order, but find it somewhere. Take a second to do so. It's 1 over x. This one has all kinds of cool stuff. We do a whole lot of rational function work, not too long from now, and we'll talk about vertical asymptotes whenever you divide by 0. In this case, x can't be 0, and so there's a vertical asymptote whenever there's a value of x that would cause you to divide by 0. So there's 1 and 1 over x, this reciprocal function. Then if you take and do the domain, it's broken up by that vertical asymptote. So the domain isn't negative infinity to infinity. You have to go negative infinity to 0, parenthesis, because it doesn't touch it, and then that union symbol, parentheses, 0 to infinity. If you started the My Math Lab related to this, you'll start writing domains with the union symbol and all that. Oh, it's a pain, but use the help there. Ask me for help, whatever you need. Range on this one also broken up, but by something different. It's the range of the reciprocal function is broken up by a horizontal asymptote, which sometimes the graph crosses horizontal asymptotes. Never vertical asymptotes, but sometimes horizontal asymptotes. This one has, you can see the domain. We're going off the graph, and that's kind of part of the deal, is can you read these known graphs and recognize their domains and ranges. Radical functions next, square root of x, call that a radical. Then the domain, it does touch at 0, 0, because you can put 0 into a square root. Square root of 0 is 0. So it does touch there, and that means it's a bracket 0 to infinity. And range, same thing. It starts at 0 of the low height of 0, and then goes on up. Looks like it might taper off, but it doesn't. It just gets bigger and bigger. Okay. Absolute value, there it is. There's the absolute value markings. Don't forget on your calculator, it's math num abs, because nothing numbs the abs like a little math workout. I had one this morning getting ready for you guys. It was awesome. Domain, negative infinity to infinity. And then range, it does start at 0, and then it goes up from there. So there's a bracket. All right, again, ask for pause as needed. I'm going to keep rolling with my ninja writing. If you notice how fast I can write, it's usually 2 or 3 cups of coffee, and I am good to go. Look at that. I put in a blue horizontal asymptote on the reciprocal function because I want to talk about key features of these and how to sketch it by hand. The reciprocal function is kind of centered around the origin 0, 0, and then there's these 2 asymptotes, vertical and horizontal, and then if you go from 0, 0 over 1 up 1, you can plot 2 points. After that, you just kind of let the graph bend and squish into each corner like that. It's a rough sketch. So when we do them by hand, we're going to do very sketchy sketches later. The things you want are the 2 vertical asymptotes, a point that's kind of like over 1 up 1 in both corners, opposing corners, and then you just kind of bend it into the upper right and lower left quadrants like that. Okay. Then when it comes to the radical graph, you just do 0, 0. And then from there you go over 1, up 1, and then over 4, up 2, knowing that the square root of 1 is 1, the square root of 4 is 2. Those are good, easy starting plot points to work with. And then on the absolute value, it's got slopes of 1 and negative 1 on either side. So notice those things, because when you're freehanding it, you're going to think, how can I recreate that graph? What do I need to remember to get a decent sketch? And those are the things I'm highlighting there. Okay. Next, exponential. Hopefully that's the order of your notes. I have no idea. E to the x is standard. Sometimes it's 2 to the x. It could be any base to the x. And so let me add to that. It could be, 2. Whoa. Highlighter's not going to help. 2 to the x is an exponential. 3 to, hey, any base number that's to the x power, that'd be considered an exponential. E to the x is just your famous Euler's number, and it has cool properties, and we'll talk about that later. Domain, left and right all the way, any x is possible. However, the range does 0 to infinity, not including 0, so there's a parenthesis there. It does start at 0. There's an asymptote, horizontal asymptote, and exponential functions are always positive. That's another cool feature of those. We're going to go next to logarithmic. We can do log of x, which is base 10, or ln of x, which is base e. We'll elaborate on that later. You may remember. They look very similar for our sketching purposes. You won't need to worry about what the difference is sketch-wise at this point. Domain, it starts at 0, doesn't touch 0. There's a vertical asymptote, and that actually becomes its key feature with a logarithmic function has a vertical asymptote. The exponential has a horizontal asymptote, and we want to remember that. The range on that one, it does go all the way down as you get closer to the y-axis. If you kind of peek in there, it does get really snugly up against there, but the graph just keeps going down forever. And then it goes up forever. So that range is all real numbers, negative infinity to infinity. The domain, though, 0 to infinity. Make sure you notice it is not a bracket. It doesn't touch there. Okay. Cool thing about these two is they are inverses of one another. That's what makes exponential and logarithmic. So if it's e to the x and ln of x, those are specifically the ones we use a lot. They are inverses of each other. Okay. They undo each other algebraically. Actually, I'm going to write here, inverses undo each other algebraically. So we will use them to kind of solve in equations with logs and exponents. We use one to undo the other. But graphically, what's cool about them is they're mirror images of each other over the line y equals x, the linear equation that we started with. That's something we can elaborate on later. But they also, if you remember when you do an inverse function, do you remember you swap x and y and solve for y? I know a number of students remember that from Algebra 2. You swap the x and y coordinates and solve, and you get what's called the inverse function. Well, that's what these are. You would swap x and y and solve, and when you swap x and y, you're also trading the domain and range, which tells you about what x's and y's are possible. And things all everything about x and y trade. Instead of a vertical asymptote, we have a horizontal asymptote, and vice versa. We have the domain and range swap. So inverse functions are neat that way. They swap their x and y stuff, and they undo each other. Last one on that line is a logistic. This is one form of it that I've written there, 1 over 1 plus e to the negative x. There's a couple other ways to look at it. My favorite is lice minus licht. I'll tell you about that later. Then negative infinity to infinity, domain left and right is infinite, and there are 2 asymptotes, 2 horizontal asymptotes in this that the graph snuggles with. And so with my range, it goes between the asymptotes, which is 0 to 1 in that first picture, But sometimes, I threw in the other form over there. You can take a second to look at it. The other form is very similar. It just has an L on top and some other variables inside there, but it's more similar than you want to think it is. It looks crazy, I'm sure, at this point. But the L on top actually has to do with where the top is, where the upper bound, the growth constant up here, that L would be wherever that top horizontal asymptote is located. And that's a neat feature about it, is whatever number you put on top of this function tells you where the top of that logistic curve is, a S on the side. This is used for population growth, because you all may have, I'm sure you've learned in some biology class that populations grow exponentially, which this graph has that behavior, but it grows exponentially until whatever it's needed to sustain that population, food and other resources, are depleted, and then that population will cap. They can't go beyond the resources available to that population. Logistic is a way of modeling that. So sine and cosine, oh, you know these. I'm sure you have dreamt about the day these would come back. Sine, it starts at the origin and goes up and down. And then has all real numbers, but the range, it goes between -1 and 1. It does hit at those heights, so there's brackets involved. Cosine is a little shift left or right of that sine curve. Same domain and same range. They're just, really, sometimes there are folks out there that never use both. They just stick to one, but they have cool properties, so we like to see both. There's the floor function, the step or the integer function. All of these are descriptors of this last